Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to a new discussion on this applications of DEMs in solar and wind energy potential estimations. As you know that basically DM represents terrain, and the same terrain can be further analyzed for solar and wind energy potential estimations. Because as you know that for example that south facing slopes will receive sunshine almost an entire day, especially in the hilly terrain like Himalaya. And that is why you would also see that lot of developments in the hill regions in past, even current, are all taking place mainly on the south facing slopes. So, south facing slopes are very important from solar energy point of view. But still there are some other directional slopes, because every slope is not having a south facing direction. So, there will be some other directions. So, how can we estimate what is the potential if at all a solar power plant has to be established? This is being done extensively, I know, in these hilly states, especially in Uttarakhand, and lot of such projects are coming. So, how we can exploit digital elevation models in GIS to estimate solar and wind energy? But before that, very briefly I will touch about certain fundamentals. As you can see that of course the source of solar energy is sun, and that is in two forms. One is in the radiation form, which is what it is required for the solar panels, and another one is the thermal one, which basically provides the heat, and that too is being exploited again in hilly regions where winters are very cold for these solar water heater or plants. So, both the components of the solar energy can be exploited, but where to install, that is what we are going to discuss, and what are the complications will arise. So, if you see that there is a sun and that energy is available, so if a sky, theoretically, if a sky is clear, then the radiation will reach directly to the surface without any hindrance, but we know that it is not like that. And if it is cloudy or some substances are present or gases are present in the atmosphere, then instead of getting direct radiation, we get the diffuse radiation. And sometimes also in hilly regions, we also get a radiation which is we can put in a category which is called reflected radiation. So, this incoming solar radiation, or in short we say insolation, provides from the sun, and this insolation it is as you know is modified when it travels through the atmosphere from the sun towards the earth, and also it is modified by the topography as just mentioned, because of instead of not receiving direct reflection or direct energy, we get the reflected energy. So, it is further modified by topography and surface features. Surface features might be vegetation, might be agricultural crops, or the soil conditions also. And finally, of course, the lithology also play. Different types of rocks will behave differently from solar energy point of view. So, the solar radiation which is coming before it reaches to the earth, it is intercepted at various places. Sometimes you get the direct, but rarely, only in a very special circumstances. Still you generally you get the diffuse one, and then of course In the hilly parts, you get lot of solar energy through the reflected components. Now, this direct radiation, as we have just mentioned, that this is intercepted and uni-impeded. That is the basically uni-impeded means that the direct line from the sun. So, this impeded problem will always be there, because there is a thick atmosphere between the sun and the earth. But they say if we talk about say Mars or a moon surface, where the like in Mars there is a very thin atmosphere, and therefore the solar energy can reach unimpeded at the surface of the Mars, but not like on the surface of the earth, because luckily we are having atmosphere, and that atmosphere basically because of that the life exists on the earth. So, in some way, but from solar energy point of view, this atmosphere is a kind of hindrance. Nonetheless, so this diffuse, instead of direct radiation, what we are getting diffuse radiation, which is scattered by atmospheric constituents. There may be many constituents, clouds, dust, gases, and so many other components are there, and dust of different sizes, particles of different sizes. Now, the third component, that is the reflected radiation, is reflected from the surface features, and as I have mentioned that in hilly regions this component is also quite significant, because for solar energy, even if a reflected radiation is there, still you can generate some energy. It is not necessary, what I mean is that it is not necessary that you should always get a direct sunlight on solar panels, then only it will generate energy. You recall the usage of calculators we used to have, in which a small solar panel used to be there. That solar panel or those calculators used to work even in a tube light. So, a small radiation which is required for that kind of operation is available even in natural light, may not be directly in the sun. So, the total sum, the sum of the direct, diffuse and reflected radiation, which we call as a total or global solar radiation. So, this global solar radiation, lot of these estimations about potential of solar energy can be based on this global solar radiation, rather than looking for individual components. Now, further, that generally this direct radiation as you know is the largest component of total radiation, because that is how this energy is reaching, though in between there is a atmosphere, but still it is the having major role towards the solar energy generation. And the second position is held by this diffuse radiation, and of course reflected radiation will have the third one. Now, this reflected radiation constitutes only a small portion of the total radiation, except for locations surrounded by highly reflected surfaces as a snow cover. So, in these areas which are covered with the snow or glaciers, where reflection is very high, their reflected radiation can be also of very significant amount. And generally the solar radiation techniques or tools to analyze in GIS, they do not include the reflected radiation in calculation of total radiation. So, obviously it will estimate for a certain location, but whether this real thing in real conditions, what would happen, because what you are doing with GIS is doing a modeling part. So, obviously and the modeling and the real world, there are always difference in these models. Nonetheless, we can extensively, and it is being exploited extensively, GIS tools are being exploited to get these estimations about solar energy, potential of solar energy associated with a particular location. So, what we do, as I have just also mentioned, that the total radiation is calculated as the sum of the direct and diffuse radiation. Now, this solar radiation calculation for point locations or for an area, we can do it on a GIS platform, which will involve 4 steps. The first step is the calculation of upward looking hemispherical view set. View set part we have already discussed. Think a view set which is looking towards the sky. That is why the word upward looking, and hemispherical because you cannot see the entire hemisphere from a single point or an area. So, these 3 words are important, that upward looking hemispherical view set based on the topography. If somebody is located in a valley, then this view set is going to be very narrow. Though these 2 conditions will be there, but still view set is going to be narrow. But if somebody is top of the hill or on a peak, then naturally the view set is going to be very high. So, it will depends on the topography. Now, what we do, we overlay of the view set which will be calculated keeping upward looking and hemispherical on a direct sun map to estimate the direct solar radiation, and the overlay of view set on a diffuse sky map to estimate diffuse radiation. So, we can also calculate not only the direct radiation, but also the diffuse radiation. And the final step in this solar radiation calculation or analysis on GIS platform is this: we repeat this process for every location of interest to produce an insolation map. So, in that way we can achieve this estimation of solar energy potential about a location or a particular point or an area. Now, as we know that the radiation can be greatly affected by topography and the surface features, and therefore, a key component in the calculation of this algorithm which requires the generation of upward looking hemispherical view set for every location in the digital elevation model. So, for every location it is will be done. That means every location here means every cell of our grid, that is digital elevation model. So, this hemispherical view set basically if you think they are similar to the upward looking hemispherical or fisheye photographs. That means a very wide angle view would be available, which view the entire sky from the ground up, similar to the view in the planetarium. So, we can if we are located, if that location for which we are going to do the estimation is in a open part like on a hilltop or on a ridge, but if I am located in the valley, then scenario is going to be the different. So, now this is what is the fisheye view or upward looking hemispherical. A photograph was taken keeping the camera on the ground, and this is how it looks. So, providing a view of the visible sky and the sky directions obstructed by the surrounding. That is why it was mentioned that not only the topography affects the solar radiation, incoming solar radiation or insolation, but also the features. So, like features in the here, they are also creating hindrance here. So, they are not allowing us to have a complete upward looking hemisphere rather than a hindered one through because of these ground features. So, topography and surface features, they may create problem. If I am in the valley, then I might be having this curtailed view like this. So, something like that. Now, this is similar to the view you would have from the ground looking up on all directions, that is the fisheye view. Now, how much amount of visible sky plays an important role in the insolation at a location. So, this will play a very important role. Again, this upward hemispherical view set can also be used to plan GPS campaign in a hilly terrain. Because for a GNSS or GPS based surveys, again you require a sort of, in that terminology they say sky plot. So, you require a upward looking hemisphere, and that should be clear. As clear the sky would be or sky plot, you would have a better signals or signals from many satellites. So, if somebody is going in a hilly terrain and area is fixed, then when you are having a quite reasonably good digital elevation model, then before reaching to the ground, one can really plan that what is going to be this upward looking hemispherical view set for the antenna of your GNSS device or GPS device. So, there also the similar kind of calculations can help this upward looking hemispherical view set. So, a sensor, if a sensor located in an open field like in case of GNSS has a higher insulation than a sensor located in the deep canyon. Now, instead of sensor, one can have a solar panel that is also in many ways a receptor. So, it receives the solar energy. So, if it is kept in open sky or in open area, definitely it will have more energy which will be reaching to that sensor or receptor or device. Now, view set as because we are handling in the raster or grid. So, this view set is a basically raster representation because the basic input data is digital elevation model which is grid or raster. And that so the view set is a raster representation of the entire sky that is visible or obstructed when the view set from a particular location. So, you get a complete picture. Now, this view set is calculated by searching a specified number of directions around the location of interest. Now, one can search the entire sky or one can search in a particular direction, and this will determining the maximum angle of sky obstruction and horizon angle also. Whether parallel to horizon you can get the signals or energy which is generally it's not possible. So, what angle you would like to have above, say above horizon 5 degree, 10 degree, this much 5 degree minimum is always, this cutoff is always required. Otherwise, for on edges you will not have anything, and for all other these unsearched locations or directions, horizons angles are interpolated. So, all these things are done. Now, this horizon angles are then converted into hemispherical coordinates system and thus representing the 3-dimensional hemispheres of the directions of 2-dimensional raster image. So, when I show the examples, these things will become further clear to us that that raster cell of your or grid cell of a digital elevation model of the view set is assigned a value that will represent the sky direction which is visible or obstructed, and then output cell locations, that means the row and columns, correspond to the zenith angle, that is theta, and this zenith angle is basically the angle relative to straight upward, and azimuth angle with reference to the north, that is the alpha, angle relative to north on the hemisphere direction. So, this is though it would be in raster form, but the representation is little different than what we see. Now, when we involve a digital elevation model and this kind of estimations of solar energy, here what we are doing that there are so many directions instead of 8 directions, now we are having 12 direction here. So, for 12 directions the calculation is being done, and based on the location, that means because digital elevation model is also providing the information about the terrain, and that is why you are seeing that there are some shaded areas and some is the open. So, at that particular location, this is the open area is having, and if we compare with this camera fisheye view, this is what we are seeing. So, these are the areas where hindrances or features, ground features are creating problem. So, with this this input or start, now we can add this we can add a cutoff for this horizon angles, which are calculated a specified number of directions, whether you want to have all 360 degree or in a specified direction, and used to create a hemispherical representation of the sky. And what ultimately you would get a view set characterizes whether sky directions are visible shown in white or obstructed shown in grey. And this is what here that this white part is completely visible, whereas these grey parts are obstructed. And this view set which you are seeing in the center is shown overlaid on the hemispherical photograph to demonstrate the theory. So, if you are having that one foci, this is just to check, but your estimations in GIS and for solar, this upward hemisphere will provide this kind of output. Now, in further this calculation, we have to also calculate one important thing, which is sun map calculation. So, after getting this information about how much part is going to be obstructed because of features present or topography, then next step is the sun map calculation. So, this direct solar radiation originating from each sky direction is calculated using a sun map. Now, remember this thing that the relative to sun, the position of the sun is changing. So, these are all dynamic things. So, that if we want a more accurate estimations about against a particular location or an area, then all those things have to be kept in mind while doing the calculation. So, in the same hemispherical projection as the view set. Now, this sun map is again everything is being done in the raster. So, sun map is a raster representation displaying the sun track, because now we are involving the sun from morning to evening. So, that is why I was saying earlier that when relative to the earth, the position of the sun keep changing because earth rotates. So, the sun track or apparent position of the sun as it varies through the hours of the day and through the days of the year, because seasonal effects will also play a very important role. So, these things are also considered while doing the sun map calculation, and this it is like similar to what you are looking up and watching as the sun positions moves across the sky over a period of time. So, that sun map calculation will consider all this, and that is in the daytime how the sun is changing with reference to that particular location, and also in seasons, because in winter seasons sun is having larger distance from the earth, and therefore there are changes. Now, this sun map will consist of discrete sun map sectors defined by the sun's position at a particular intervals during the day, hours and time of the year. So, this much information we will get from this sun map, and this sun track is calculated basically. Sun map will consist sun track, which is calculated based on the latitude where it is located, your area of interest of the study area, and time configuration that defines sun map sectors. And for each sun map sector, there will be sectors, not like your a cell, but sectors in a view set, and that is hemispherical view set, or in that projection a unique identification value is specified along with its centroid, zenith and azimuth angle. So, this much of information is very much required, because for any that location then you will get all detailed information, and then the solar radiation originating from each sector is calculated separately, and then finally the view set is overlaid on the sun map for calculation of direct radiation. Why overlaid? The view set is overlaid because the hindrances which we are being caused by the ground features or topography, they have to be also discarded because of you do not have the information or sunlight reaching from those areas because of vegetation, topography and other thing. So, then it is overlaid. So, this is what you are seeing. This is a sun map for a north 45-degree latitude, calculated from the winter solstice, that is the December 21st, to the summer solstice, that is June 21st. So between these, as you can also see that between, so after this you are having June 22 and you are having December 22nd. Now in between all these sectors are representing all that information which we have just discussed. Of course, the hindrance part is not yet here, the effect of topography and features which will also come. So each sun sector, these are the sun sectors which you are seeing here. Each rectangle which are different colors represent the sun's position using half-hour intervals. Every half an hour you are having. Because if we go for less than in this half an hour, then you will have maybe of less size of these rectangles or square. And so sun's position using half-hour intervals through the day and monthly intervals through the year. So all these information will be generated, and it should be here we noted that the image which you are seeing is the same hemispherical projection. Of course, because we are projecting using this hemispherical concept, because the point here that it is upward looking hemispherical. So that is why everything will be in the same projection as upward looking view set. Now this the position of the sun is represented as it moves across the sky during the time of the day, and so different timings are there. See, this is 0050, and then here you are having 19 hours in the evening time. So how it will move, and the position of the sun is represented like this. So you get both the information that with the in a year how things will change, and how with the daytime how things will change throughout the day. So if I take an example of say this is example it is given here. So if I start say, of course like 10 o'clock, 10 a.m. Now 10 a.m. in a say month of February or March or June, say in the May. So in the, that means this is the position of the sun in the May. So this is how you will get this sun map will depict all these details here. Hindrance is not yet, that will also come. Now this sky map, this is the same term which is used in GNSS technology or GPS, is that how much sky is open. So this diffuse radiation originates from all directions, sky directions, as a result of scattering by the atmospheric components. And these components I have already discussed are like, for example, clouds, dust particles or gases or other particles also. So this the calculation of this diffuse radiation for a particular location, a sky map is created, and a sky map is nothing but the upward looking view set to represent a hemispherical view of the entire sky divided into series of sky sectors defined by zenith and azimuth angles, and that you will see. And these each sector is assigned a unique identifier values along with the centroid, zenith and this. And this diffuse radiation is calculated for it. So earlier we have been calculating for direct radiation, now we are calculating for diffuse radiation, because the final product, final calculation has to include both, or rather if more accuracy is required, all three components of radiation, that is direct, diffuse and reflected also. But in order to model that reflected part, that is not that easy, because it depends on the surface conditions. Like gave the example in the snow or glacier covered areas, and the reflection may be different. In a forest covered area, diffraction may be different. In bare grounds, that reflection is going to be different. So for entire 360 degree, a sky map with the sky sector defined by 8 zenith divisions which are there and 16 azimuth divisions are there. So, one is this division, then azimuth division, another one, another one, another one, likewise. And 8 means if you start from center 1, 2, 3, 4, 5, 6, 7, 8. So, these are the 8 divisions. So, now you are having sky map and you are also having sun map, you are also having view set. Only thing now these things have to be combined now. So, each color as you are seeing in the left image is a sky sector or a portion of sky from which diffuse radiation originates. And just recall that when we have been discussing about direct radiation, and we had a limited hemispherical projection for direct radiation because it is not available from all directions. That is why it is just a band in this view set is available to us. Whereas when we come to this diffuse radiation, then it is being estimated from all directions. It is assumed that diffuse radiation will reach from all directions. So, that is why this kind of calculation is being done. So, now overlaying the view set, that view set which was representing our hindrances with the sun map and sky map, when we overlay all these three on a GIS platform, so that means that during the insolation calculation, the view set raster is overlaid by the sun map and the sky map rasters to calculate diffuse and direct radiation received from each sky direction. And the portions of visible sky area in each sector is calculated by dividing the number of unobstructed cells by the total number of cells in each sector. And this will basically allow us to mate for partially obstructed sky sectors. So, here is this is our sun map with obstructions information, and this is our sky map again with the obstructions information. So, when we overlay all this, so overlay of a view set on a sun map or in a sky map, of course, the grey areas represents the obstructed area. So, solar radiation, this is for the direct and this is for the diffused. Now, the solar radiation is calculated by summing of direct and diffuse radiation. Of course, one more component, that is the reflected one, but somehow it is not easy in this modeling part to do that. So, that insolation originating from the unobstructed sky directions. So, obstructed part are already shown in grayscale. So, whatever the open sky is there or unobstructed sky is there, that is one which we are getting. So, with this we can get a very detailed information about from where the direct solar radiation will be reaching to a particular location, point location or an area for which the calculations can be done, including about the obstructions. And same with the sky map, from where things would be available and not. And again you can overlay with the obstruction map also or that view set. So, now what are the applications? Some of the applications we have already touched, but nonetheless for completeness I will go one by one, that this incoming solar radiation, that is insolation, is the basically driving force of the Earth's physical and biological systems. And knowledge, if we are having good information about any area about this kind of information about direct or indirect solar radiation, then that can really help to do lot of other work for energy generation or thermal or other parts. So, the amount of insolation at a specified geographic location is helpful for applications of diverse fields. Even nowadays, people who are developing resorts in hilly areas, they too are interested to know that how much sun and when they will get. That is that is very, very important in especially where the cold months are many. For about 6 months or 8 months you are having winter, and therefore the sun becomes very, very important. So, this the applications are in the landscape ecology, in the meteorology, even in agriculture. because for agriculture practices you require sun. So, if somebody is developing a farm like that and in a hilly terrain where topography can create hindrance, then that modeling can also be done. Of course, environmental modeling, agriculture, forestry I have just mentioned, and solar energy generation estimation. There it is being used maximum. And of course, for GPS campaign in hilly areas, which people can plan before really they reach to the ground. So, they will know what kind of sky plot or open sky they will have, what kind of hindrances they are going to have. Of course, this is non-exhaustive list that this new applications will keep coming in this one. Now, applications of this solar radiation which we are having, that knowledge of how much sun an area receives over a period of time may be useful for determining new sites for ski resorts, because how long this snow will remain in that area will also depend how much sun it receives, and best locations for growing especially crops where specified microclimatic conditions are needed for optimal growth. And another example of this solar energy or solar insolation maps is that important for predicting behavior of forest fires, because there also it provides the heat and that can also create sometimes there are natural forest fires. So, that also can be assessed and making decision based on that information for the best fire fighting methods. So, for that purpose also it can be done. Now, in the civil engineering and urban planning, insulation can be important input for suitability models used for determining optimal sites. Nowadays, there is a demand for zero energy or low energy buildings or infrastructure, and that if in daytime, if for lighting purpose, if we can avoid, wonderful. If in cold areas, if heating can be avoided or with minimum heating things can be done with the solar insulation, that would be again wonderful. So, lot of now emphasis is on that how to design buildings or these infrastructures which will require the minimum energy and maximum dependence can be made on solar. Now, so if I have to do it on multiple locations, that can also be done. Like here, the locations, there are 4 locations have been chosen, and a maximum crop growth and that crop growth must be determined. There are many other such applications are there, and one can have the direct and diffuse radiation calculation for multiple locations. Of course, the season will also play very important role. Now, this global insulation calculations for each site located can be done. So, for like here we get the analysis for all these sites which we are I have just shown in the previous diagram. And if we want more precise analysis, of course, always there will be a requirement of high resolution digital elevation model and more detailed information about the features and other things. If that information is available, then or land use and especially the height of the objects which are surrounding, not only the topography or natural objects, but artificial objects. So, if that information is there, more precise calculations can also be done. And these basically these will result, all this precise analysis would result to readily generated generalized by part more sophisticated models to determine optimum location for growing grapes across a geographic region. So, for different kind of crops the requirements of sun is different, and therefore, such things can also be planned. In last few more minutes I would like to spend on wind energy, because in a hilly terrain again wind energy plays because this topography will play very important role in case of a hilly region. In flat areas things may be different. So, wind energy, the large areas are being screening that can be done usually begins with the review of existing wind resources maps, data and other meteorological information. Meteorological information especially about the prevailing wind direction and wind speed, and other informations might be atmospheric pressures, temperature, etc. And then this analysis of climatology of a region along with the topography. So there comes the role of a digital elevation model. That terrain data is very much required. If it is a flat terrain, I am telling that then it is may not play a very important role. But if it is a hilly region, obviously it will play very important role. Now this is a very wind power density map, or it's a potential kind of thing. So this is the wind power which is available in different parts of the country. As you can see that the maximum part is available, which is the wind which is coming from Arabian Sea. So you see many parts of Gujarat, and then Maharashtra, and then other states like Tamil Nadu and Kerala, all those parts, and also a large part in Rajasthan. There a lot of wind farms have come, and there you can see that installable, this is the potential which has been estimated. Of course, in this calculation, the digital elevation model has played a very important role. But if somebody is doing this kind of calculation or estimation for a country level, like for India, is basically like a continent, and therefore it must have been done on relatively low resolution digital elevation model. But for a particular site, like if we see, we focus on the Uttarakhand part, there are few areas. So that means that if I want to make sure that if I am going to invest for wind energy in these areas, I will do the analysis again with high spatial resolution digital elevation model, and then will get more accurate. But overall, a map is quite useful, that these are the regions of India which is having a good potential for wind energy. Similarly, this wind power density map at 80 meter AGL above ground level is also, because these wind turbines, they are generally installed above the ground. So from because at the ground level the wind energy may be different, whereas at the 80 meter the wind energy may be different. So a offset, basically offset in this whole topography has been added, because there will be hindrances because of forest or other things. So that offset map is also there, which is again, it is basically enlarging the area. So if you compare with previous map, say if I concentrate only on the Gujarat part, so at 50 meter ground level this is the situation, and at 80 meter ground level almost entire Gujarat is having great potential. So basically the purpose of GIS is to model things, to predict things for different scenarios. Here two scenarios, 80 meter, 50 meter. So if a wind turbine is installed at 80 meter height, then almost entire Gujarat can be exploited. So of course the cost will be different. So in these areas 50 meter, at the coastal areas 50 meter height turbines would be sufficient, but here 80 meter. So definitely at 80 meter the potential increased significantly in some areas. So this is the basically this WT wind power development map of India at 50 meter level. This you can also see the updated one on the internet, and basically also wind turbines are here, wind turbines are shown here, that how the topography affects, because in certain regions. So topography plays very important role. As you can see that this is all hills are there. So in order to exploit that the wind along the hill or foothills, this is what the wind tunnels have been put there. Even in the valleys there sometimes this effect is there of energy. which I have observed near Lakshman Jhula. In early morning hours, every day there is a good wind, and then by 9 o'clock or 10 o'clock things settle down. So even if energy can be exploited for few hours in a day, what is the problem? Because after all, it's a free energy, renewable energy. So wind energy is a very, very important, like solar energy. These are non-renewable. You don't have these are renewable basically. So you have got this potential, so much potential in India, especially about the solar. Further, it can be exploited by employing digital elevation models and GIS. So with this, I end this discussion. Thank you very much.